Welcome back. Today, we're going to tackle a hard-level LeetCode problem, number 42. Let's take our time and walk through it carefully. Here's the prompt. Given n non-negative integers representing an elevation map where the width of each bar is 1, compute how much water it can trap after raining. We're given an array where each element represents the height of a vertical bar. Our task is to figure out how much rainwater can be trapped between these bars after a storm. You can clearly see that the rainwater gets trapped between the walls. Let's look at the first position. There's no wall to the left, so of course, no water can be trapped here. At the third position, we can see 1 unit of water. Why? Because there's a wall of height 1 on the left and a wall of height 2 on the right. Since the left wall is shorter, we can only trap a single unit of water in that spot. No more. Now take a look at the 6th bar. This shows that even across a wider area, water can still be trapped. Can you start to see the rule here? At any given position, the amount of water it can hold depends on the tallest wall to the left and the tallest wall to the right. The water can only rise as high as the shorter of those two walls. And here's the nice part. We don't care how the walls in between are shaped, just the tallest on each side. So if we know left max height and right max height for each position, then the water trapped at that position is simply min left max height, right max height, minus current height. In this example, a total of 6 units of water can be trapped. Now, let's apply this approach to solve the problem step by step. First, we need to record the highest wall to the left of each position. We'll start from the far left and move 1 step at a time to the right. At each step, we'll keep track of the highest wall we've seen so far. At every index, we'll record max height as the left max, and then update max height if the current wall is taller. So we start at position 0. The height here is 1, so we record that in max height and move to the next position. That gives us a left max of 1 here, and then we continue. As we go along, we're building up a list of the tallest left side walls seen so far for each position. Once we've completed the left max list, we're going to do the same thing, but this time from the right side. And at each step, we keep track of the highest wall seen so far from the right. This gives us the right max list. Now that we have both the left max list and the right max list, we have all the information we need to calculate the amount of water trapped at each position. Let's walk through how we compute the total. Now, let's go from left to right. At each position, we take the smaller of the left and right max heights and subtract the height of the current bar. So, at position 0, min left max, right max is 0, and the current height is also 0. So 0 minus 0 is 0. We add that to total water. At the next position, the smaller of the two max values is still 0. But the current height is 1. That gives us negative 1, which doesn't make sense for trapped water. So if the result is negative, we just treat it as 0. We continue this process for each position. And at the end, we'll have our total trapped water. In the example we've been using, the total comes out to 6. Not too bad, right? Again, the key idea here is that at any position, the amount of water you can trap is limited by the shorter of the tallest walls on either side. Now let's implement this logic in code. First, let's initialize what we need. We'll store the length of the input array as n. Then we'll create 2 arrays. Left max list to store the tallest wall to the left of each position, right max list to store the tallest wall to the right of each position. Now let's fill out the left max list first. We'll loop through the array from left to right. For each position, we get the current height and store it in a variable called current height. At that point, the tallest wall to the left is stored in max height. We update left max list I with the current max height, and then we update max height if current height is larger. We repeat the same process for the right max list, but this time we move from right to left. At each step, we track the tallest wall we've seen so far from the right side and store that value into the list. Once both of these arrays are fully built, we're ready to calculate the total amount of water. We'll initialize a variable, total water, to 0, and loop through the entire array again. At each position, we take the minimum of left max and right max, subtract the current height, and if that result is greater than 0, we add it to total water. After going through every index, we return total water. Let's run the code and see the result. Looks good, right? This method loops through the array 3 times, once to fill left max list, once for right max list, and once to calculate the result. So the time complexity is O of n. Since we use 2 additional arrays of size n, the space complexity is also O of m. But what if we want to improve the space complexity? Let's take a look at a more optimized solution using constant space, O of 1, without using extra arrays. We're going to use a technique called the 2-pointer approach. We place one pointer at the left end of the array and another at the right end. The left pointer moves to the right and the right pointer moves to the left until the 2 pointers meet. While we do this, we don't store all the max heights in arrays. We simply keep track of the tallest wall we've seen so far on each side. Left pointer starts at index 0 and the right pointer is at index 11. We already know that no water can be trapped at the very edges of the array. So what do we do next? Here's the key idea. We always move the pointer with the smaller max height. Why? Let's think about a general case. Suppose we have our left and right pointers positioned like this. Left max is currently less than right max. Now, since the left pointer has moved from the far left up to this point, left max must be somewhere in that section. Likewise, the right pointer has moved from the far right to this point, so right max must lie within that range. Then, in terms of where water can definitely be trapped, we can be sure about this region only. At this point, can we calculate how much water is trapped at the right pointer? Not really, because we don't know the wall heights between the left and right pointers. So we can't be certain whether water can be trapped at the right side. On the other hand, on the left side, regardless of what kind of walls exist between the left and right pointers, we can be sure that water can be trapped up to the left max level. That's because water is always trapped up to the smaller of the 2 maxima, left max and right max. Since we take the min, left max, right max. To compute the water level, only the smaller value matters. It doesn't matter whether the larger value is 100 or even 1000. As long as we know the smaller one, the trapped water level is determined. So once you understand this principle, this 2-pointer method becomes very straightforward. Now, let's go back to our example. Right now, left max is smaller than right max. So we move the left pointer 1 step to the right. Let's calculate how much water we can trap at this position. We use the same formula. Min, left max, right max, minus current height. Since left max is smaller, the minimum is just left max, which is 0. And the current height at the new position is 1. 0 minus 1 gives us a negative number, and of course, we can't trap negative water. So we just treat it as 0. Now let's update left max with the height at this new position. It becomes 1. Next, we compare left max and right max again. This time, they're equal. When both sides are equal, we can move either pointer. It doesn't matter. Let's just keep going with the left pointer. We move it 1 step right again. At this position, left max is still 1, and the current height is 0. So 1 minus 0 is 1, meaning we can trap 1 unit of water here. We add that to total water. We keep going. Now left max is 2 and right max is 1. Right max is smaller. That means we move the right pointer 1 step to the left. At this new right position, right max is 1 and the current height is 2. 1 minus 2 is negative, so again, no water is trapped. We skip it. We continue this process, moving whichever side has the smaller max height. calculating how much water can be trapped at that step and adding it to the total. We repeat this until the 2 pointers meet in the middle. And that's it. That's the two-pointer approach in action. Now let's implement the code. We start by initializing 2 pointers, left index and right index. We also initialize left max and right max using the heights at the current left index and right index positions, respectively. Then we enter a while loop that runs until the left and right pointers meet. Inside the loop, the first step is to update left max and right max based in the current heights at the respective positions. Next, we compare left max and right max to determine which side has the smaller maximum height. If left max is smaller, we move the left pointer 1 step to the right. At this new left position, we calculate how much water can be trapped. We subtract the height at the current left index from left max. Otherwise, if right max is smaller or equal, we move the right pointer 1 step to the left. We then calculate the water trapped at this right position in the same way. When the left and right pointers finally meet, we've scanned every position where water could be trapped, and we simply return total water. Let's run the code now. Voila! This solution doesn't require any extra arrays, and it still runs in linear time, ON. Much more space efficient, right? That's the power of the 2-pointer technique. Nice job following through. The most important takeaway from this problem is the intuition that, at any position, water can only be trapped up to the height of the shorter wall on either side. If this video helped you understand the concept, don't forget to like, subscribe for more algorithm deep dives like this. Thanks for watching, and I'll see you in the next one.